Hello. I hope you can hear us properly, and nice to be here. We come from eRoots Analytics, a Spanish startup, and we'll be presenting open source cutting-edge algorithms for modern grids. And so I have to recognize that this title could be quite open, and pretty much all the summit revolves around this topic, but we will narrow it down very quickly. And so the first question we should ask ourselves is, why should we even care about simulations? I would say that simulations as old as power systems. Initially, power systems engineers would require calculations that could be performed by hand, for example. And then since the advent of the digital computer, we have had software for power systems. You see the picture here. This was more than 40 years ago. So power system simulators are nothing new. They have existed for many decades here. And so if simulations have to be there because we need the calculations to exist, then why should we even care about producing new software? This is the context that we are in. So first of all, we see that there's quite a lot of legacy. By legacy, we mean that closed source solutions, which I will not name here, but they run on Windows machines for the most part. They are very hard to scale with hardware. And so that's a bottleneck, that's a problem. Secondly, we also have blindness. If you want to connect to the network, one of your assets, then you barely know what's going on there. And finally, grid complexity. Grid complexity has been exacerbated by the integration of power electronics devices, mainly coming from renewables, storage, HVDC, and so on. So if you have a software that can only model synchronous machines, then you are in big trouble whenever you face these modern grids. And this is why we created BetterGrid. Probably this icon rings a bell to you. This was originally called GridCal. And GridCal or BetterGrid is a power system solution that aims to be integrated fully, meaning that we have a scripting, we can work as an API, we have a graphical user interface, and all the algorithms that we would need. And we mentioned previously that it has to scale with hardware. This is really the case here. So we can run it on a microcomputer, for example, for very small projects, or we can also move to a supercomputer. This is not fake. This is, by the way, something that we have implemented. It is now currently running on the Barcelona Supercomputing Center. So how does it work internally? What's the magic of it? Well, we have a database. We have a unified database. It's not like we have many blocks around and we try to patch them all together. We have a unified database that includes time series seamlessly. And then we have many algorithms that run on that. Of course, we come mostly from the planning side of things, so state calculations, meaning power flows, linear, nonlinear, everything that you would need. Stochastic power flows, then also OPF, again, linear, nonlinear, including time series, and many other functionalities like voltage collapse calculations, short circuits, investment analysis. And now we are also moving towards the operation, meaning that we are including RMS calculations and soon EMT. I think that one of the caveats probably of most open source solutions is that they do not include a user interface. And probably we all believe that we are developers and we are programmers, and that's all good, but in the real world, most companies do not have this expertise. And this is why you really need a user interface. So from the get-go, we really wanted users to have the ability to open a software and then be able to run everything in there without having to care about the backend. And this is what BetterGrid is providing. So we have maps, for example. You can draw pretty much everything that you want. You can have the detailed schematics of the model. Then you can also inspect the database. You can include any script that you would like, and you can inspect as well the results. And so to showcase that this is, again, not fake, this is, for example, the Spanish and Portuguese grid model. And so we have here thousands of substations, many lines. And this is, by the way, the results that we are showing coming from an optimal power flow. It's oftentimes also the case that many users have to work on the same model, and collaboration is complicated. This is why we implemented a feature pretty much like Git, where you have different users working on the same model, then you save a differential file, and these team members exchange these differential files so that they all together can be merged. You can see here, for example, that we implemented some modifications in this case, some deletions, some additions. And so our team every day is merging all these files so that we can produce the Spanish grid model that you have seen. And of course, I will not forget about interoperability. We can read many, many files like PSSC, Power Factory, Mad Power, all the open ones. And since real life grids also come with errors, we have a logger and we have a debugger so that you can pick these errors and correct the network. And with that, we will go into the details of some of the most important calculations, which I will let Carlos explain.
Yeah, thank you. So I will present a couple of the tools that we have for power systems analysis in GridCal. The first one would be the AC/DC power flow calculator. This is a tool that we added recently in GridCal with the upcoming of a lot of power electronics in the grid. We thought that it was very interesting to have a very robust formulation for the AC/DC power flow so that the hybrid grids could be calculated with a reasonable computing time and with also reliability in the results. So this was, we used our own formulation in which we modeled the AC and the DC systems as a single system instead of separating the AC and the DC side and then solving sequentially, which is done in the state-of-the-art solvers. By doing this, we have to model the VSCs, which are present in the hybrid grid. And we have to enable the two controls to be able to solve the system. And these are the typical controls that we find in VSCs. And they have to be coordinated so the system can be solved. And yeah, it is solved as a single system, as I said, in a very fast time, much faster than the state-of-the-art solvers. And as I said, we model the VSCs. Not only we have them controlling the variables, but we also model the device as a branch with a quadratic loss equation. And this is how we integrate the VSC in our grid. We also have the typical power flow elements, which are the shunt elements. We use the SIP model for loads, and we also have the typical passive branches modeled as a P-equivalent line. And just to show you some results, we can see in the picture on the top how the typical solvers work. They iterate the AC system, then they find a solution, then they use this solution to solve the DC system, and they sequentially solve the system until both reach convergence. And since we only have a single system, we solve it in fewer iterations and much faster execution times. Then we jump into the other big analysis tool that we have in GridCal, in VeraGrid. So this is the optimal power flow, the AC optimal power flow or nonlinear optimal power flow. This is an expanded formulation from the typical implementation of AC OPF, which you can find probably in Mad Power as the most common open source implementation. We start from the typical power flow variables, which are the voltage, angle, and modules, and the active and reactive power generations. And we expand the formulation by using some extra variables, which are the slack variables to relax the voltage and line rating constraints. So for systems that are a bit congested, the system can be solved if the option is activated. We also include the module and phase of the tap of the transformers. So the controllable transformers can be optimized. It is treated as a continuous variable, even though typically these are discrete jumps. But we can get an optimal solution in the continuous field and then approximating it with the discrete jumps that we have in reality. This expanded formulation has to account for this relaxation of the constraints in order to avoid getting into unfeasible solutions. So we penalize the overloads in the line rate of the line ratings and the overvoltages or undervoltages of the buses. And we include it in the typical quadratic cost function for the active generation. This is an optimization problem, so what we have to do is solve the KKT conditions for those who are interested in the mathematics. And to solve this system, we need an interior point method solver, which uses the Newton-Raphson formulation. And in our case, we implemented our own implementation of the solver, so we can add some tweaks to it. And here you can see an example of a case with 300 buses. This is benchmarked against the MATPower implementation in Python, not the MATLAB one. And we can see that we have 4 different implementations of our solver because we allow for different initialization options, which typically will be using a previously executed power flow before running the OPF. And here you have a bit of the algorithm in a more schematic way of how this is solved. Finally, to talk a bit about the adoption of GridCal, last year we reached 1 million cumulative downloads, so we think this is something that people is interested in. It is also being used in the planification department of the Spanish TSO, the Red Eléctrica, and is also being used in several industrial projects around the world, and in many European research and development projects. So we envision GridCal as a tool that is constantly growing. When this million downloads was reached, many of the things we showed you today were not there. So we are constantly evolving, and we see it not only as a power system analysis tool, but also as a framework where people can design grids, treat real-life grids, such as the Spanish one we showed you, and work in projects very similarly to how GitHub projects work. And that was all from our side. Just to remind you, we have tomorrow a workshop which will be imparted by Santiago and Ryan, our colleagues, which will be at 11 a.m. in the hydrogen room. And it will revolve around executing AC/DC power flows and AC OPF. So thank you very much. And if you have any questions.